Okay, this is lesson 6.3, and in this lesson we're going to graph quadratics using x-intercepts. So we're going to graph quadratics that are in standard form, and we're going to do that by figuring out first what the x-intercepts are. And this strategy is a different strategy than if we were to complete the square and graph using vertex form. This is graphing using factored form, essentially. But we're going to get to factored form by factoring our standard form equations. And I've written some steps, and there's actually 9 steps that we're going to follow when graphing these quadratics. And we'll use them all. However, I'm going to do one example that kind of causes some problems with the 9 steps and show you how to work around those problems. But the first one is just a standard example where we'll work through all these steps. So let's take a look at the first example. I'll try to keep the steps on the screen here so we can refer back to them. It says graph the following quadratic. Y equals 3x squared plus 8x plus 5. And if we wanted to do this right now, really the only options we'd have is we could make a table and graph some points. But the problem is we don't know where the vertex is, so we might end up only getting like one arm of the parabola, and we won't really have that nice U-shaped parabola we're used to. So to avoid that, what we're going to do is first we're going to find the x-intercepts. And then we're going to try to get all the rest of the features of the parabola and graph it from all of its features: x-intercepts, vertex, axis of symmetry, and y-intercept. So how do we find the x-intercepts if we're in standard form? Well, we know that the x-intercepts will be on the x-axis, and on the x-axis, y is 0. So we can start with that. We know y is 0 at the x-intercepts. And now we're just solving this equation, which is actually what we did in the last lesson. We solved quadratic equations. How do we solve? Well, we can solve by completing the square, or we can solve by factoring. We're going to solve by factoring because we're going to find the x-intercepts. So how do we factor? Well, we look for numbers that multiply to something and add to something. The add to something step's the easy step because it's the middle number, 8. The multiplies to is usually the last number, but if there's a number in front of x, it's the last number times the first number. So it's 15. So what multiplies to 15 and adds to 8? This is one of those lucky scenarios where it's actually 3 and 5. Multiply to 15, and 3 and 5 add to 8. They're written right there. And since this isn't a simple trinomial, it doesn't just start with x squared, we have to factor using decomposition. So we're going to have to pull from our prior knowledge of last unit and remember what decomposition means. That means to break down the middle term. And we're going to break it down into 3x and 5x. Why 3x and 5x? Because 3 and 5 are the numbers that multiply to 15 and add to 8. And now we just do some grouping and common factoring. Group the first two, 3x is common, and we're left with x plus 1. Group the second two, 5 is common, and we're left with x plus 1. You'll know you factored it correctly when you get 2 brackets that look the same. And then we can rewrite it with that bracket written once, x plus 1, that's your common factor, and we're left with 3x plus 5 for our other bracket. And what do we do with these brackets? Well, we use them to find the x-intercepts. We take each bracket, set it equal to 0, and we solve it. First bracket's a little bit easier. We just move the 1 over, it becomes -1. And that's our first x-intercept, -1. Second one's a little trickier. Move the 5 over, it becomes -5. Divide both sides by 3. And we're going to get a decimal, so we're going to stick with the fraction, -5 over 3. So those are our answers to our question. If we want to write them as x-intercepts, we'd write them as points. -1, 0, because -1 gave us an answer of 0. And -5/3, 0. These are our x-intercepts. So we just finished step 1, determine the x-intercepts. Step 2 is to graph them. And graphing fractions is a little tricky, but what we'll do is we're just going to make a scale in thirds. What's that mean? Well, that means every tick is 1, 2, 3, 4, 5, 6, 7, 8, as it always was, but instead of just being 1, 2, 3, 4, 5, it's going to be 1 over 3, 2 over 3, 3 over 3, 4 over 3, 5 over 3. They're going to be fractions. And sorry, these all should have been negative. So it's negative 1, negative 2, negative 3, negative 4, negative 5. But they're thirds, so negative 1/3, negative 2/3. Negative 3/3 would just be negative 1. Negative 4/3, negative 5/3, and finally negative 2 6/3. So negative 1 is here, and negative 5/3 is here. That's step 2. Step 3 is determine the axis of symmetry. You may remember how to find the axis of symmetry. It's you take the x-intercepts and you add them and divide by 2, or since we have a graph, we can just look between the x-intercepts, and they're both one spot away from negative 4/3. So that's our axis of symmetry. The math would say take the x-intercepts and add them, and then divide by 2, but that looks a little ugly. Your calculator could handle it though, if you want to use your calculator. So there we have our axis of symmetry, and here x-intercepts. And I've boxed everything that ends up on the graph. So we've done step 3 and step 4 now. Step 5, determine the optimal value. That's where the vertex will lie on the axis of symmetry. And we do that by plugging in our x to either this equation or our factored form equation, really into either equation, it doesn't matter. I'll just use the original equation. So y equals 3, negative 4 over 3 squared, plus 8, negative 4 over 3, plus 5. And get my calculator. Let's see what we get. We get 3 bracket negative 4 over 3, and we're squared, plus 8, negative 4 over 3, and plus 5. We end up with negative 1/3. And that is going to end up on our graph too, because our vertex is made up of the axis of symmetry and our optimal value. So now we can plot the vertex. Well, since it's negative thirds, we'll make our vertical scale in thirds too. So this will be negative 1/3, negative 2/3, that'd be negative 1, and so on. So it means we got a dot right there. And now we got 3 dots. That's pretty good. Pretty close to a parabola. In fact, that might be as much as we're going to end up with. Let's see the last 3 steps. Use the c value or solve the equation when x equals 0 to find the y-intercept. Well, our y-intercept is 5. 5 is going to be way off this graph, so we can't actually use that to continue graphing. Plot the y-intercept, we can't do that, it doesn't fit on our graph. Use the step pattern or solve or axis of symmetry to improve your accuracy of graphing. Now our step pattern is over 1, up 1, over 1, up 3, over 1, up 5. So if we do that on here, over 1, up 1, we end up with this point. So that's actually following the step pattern perfectly. So let's go over 1, up 3, and that should give us our next points. Over 1, up 3. Now you might be thinking, hey, the a value is 3, so it should be 3 times bigger. It actually is 3 times bigger. It's just that the scale is 3 times smaller. So if your scale's 3 times smaller and you're stretched by a factor of 3, it really ends up just looking like the regular steps. But trust me, this is the correct parabola. And there we have some more steps, or some more points. Now, for our purposes, if I asked you to graph this parabola on, say, like a test or an assignment, using the steps to get 2 more points, I would say that that's an unnecessary step. These 3 points you had here, plus your y-intercept, and then if you reflected it, should be enough to get you your parabola. Now, because of the scale we chose, we couldn't plot our y-intercept, so I would accept these 3 points with a little bit of an extension and some arrows as a good enough parabola. So if you didn't get these points, but say you continued a little bit past and you drew your arrow here, and that little mini parabola was your answer, you would get full marks for that answer. All right, let's try another one. Example 2, graph the following quadratic. All right, we got y equals negative x squared plus 6x minus 9. Now this, because it doesn't just start with x squared, is a complex trinomial. So we'd have to factor using decomposition. I don't really want to do that though. So fortunately, we can common factor that a value. We can common factor the -1 from all these terms. It would just change all their signs. X squared minus 6x plus 9. And now we have something that we can factor like a simple trinomial. We want something that multiplies to 9 and adds to -6. And if you got a good handle on the last unit, you might notice something about this quadratic. And if not, that's okay. You'll notice it as soon as we factor it. The numbers that multiply to 9 and add -6 are -3 and -3. So we get x minus 3 and x minus 3. And those brackets are the same bracket. So we just have to write it once. And what's neat is if we're looking for x-intercepts, we're making y 0 and we're solving. There's only one bracket that we have to solve for. We only have to take that x minus 3 bracket and set it equal to 0, and we end up with x equals 3. Which means our x-intercept, there's only one. It's 3, 0. 1, 2, 3, 0. That's our x-intercept. And now if you remember back to features of your parabola, if you have only one x-intercept, that means that that x-intercept is the vertex. So this is your x-intercept and your vertex. So what that means then is that the axis of symmetry goes through your vertex. And this is nice because if we go look at all the steps that we had to do, we had to find the x-intercepts, we had to find the axis of symmetry, we had to find the optimal value, and the first 6 steps are now all done because they're all the same point. The axis of symmetry goes through our x-intercept because our x-intercept is our vertex, which means that 0 is our optimal value. But what else do we know about this? Well, we have a -9 as our y value, y-intercept. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Hey, that means we have a point right there. And if we use the symmetry, 1, 2, 3 to the axis, 1, 2, 3, we have another point. And now you have 3 points, and that's going to be enough for us to get our parabola. You could just connect these with a nice curve, and you've got your parabola. If you want to graph a little bit more precisely, we could do that because we know the step pattern. Step pattern is usually 1, 3, 5, but we have to multiply by the a value, which is -1. So our steps are -1, -3, and -5. So from here, over 1, down 1, over 1, down 1, 2, 3, and now over 1, down 5 should get us over 1, 1, 2, 3, 4, 5, to our last point. We can use symmetry to get the rest. And now you've got a nice parabola. So there you go. So if you're ever trying to graph a quadratic and you end up with only one x-intercept, that x-intercept is the vertex, and then you can graph it just like we did in unit, oh boy, it's been so long, unit 1. No, not 1, unit 4, the first unit of quadratics. So a little review on that. All right, let's flip it over and try example 3. Ooh. This one doesn't look that fun. Y equals 12x squared plus 37x minus 10. No common factors, so we can't make this look any simpler. So what are we going to do? Well, we're going to look to factor to find the x-intercepts. So we're going to ask ourselves what multiplies to something and adds to something. Our adds to is 37. What adds to 37 and multiplies to 12 times 10? Ooh, 120, but it's negative. So what multiplies to negative 120 and adds to 37? That's a tricky one. If you want to think about that, you can pause the video and try to come up with the two numbers that multiply to negative 120 and add to 37. Otherwise, I'm going to spoil it for you in about 3 seconds. 3, 2, 1. The numbers that do this are 40 and negative 3. So we can use those numbers to do some decomposition. 12x squared plus 40x minus 3x minus 10. Now we're going to group the first two terms in common factor. Looks like 4 is the greatest common factor, and there's also an x in both terms, so I'm going to do 4x. And that leaves us with 3x plus 10. What's common to the last pair is they both have negative signs, so I'm going to common factor negative 1. 3x plus 10. Our brackets ended up the same, so that means we common factored, or we factored by grouping correctly. We can take the 3x plus 10 as our common factor and 4x minus 1 as our leftover pair. And now we have factored form. What do we do with this? Well, we take each bracket, set it equal to 0 to solve for x. X plus 10 equals 0, and 4x minus 1 equals 0. Move the constant to the other side. 10 becomes negative and divides both sides by 3. And negative 10 over 3 is negative 10 over 3. And aren't we lucky we have more fractions? So our first x-intercept is negative 10 over 3, 0. And our next one, move the 1 over, 4x, divide by 4. We end up with 1/4. So our other x-intercept is 1/4, 0. And now to graph this using a fraction scale is going to be kind of tricky. So when you receive x-intercepts that have fractions, I'd say for this one, it is acceptable for you to approximate this using decimals. So this x-intercept is negative 0.25, and this one would be negative 3.3 repeating 0. So we got negative 3.3 and 0.25. Oh, not negative, positive. Why did I write negative? So let's go on here and come up with where those would be on the graph. Well, 1/4, if we do a regular scale of ones, would be right there. and negative 3.3, 1, 2, 3.3 would be right there. Which means our axis of symmetry is somewhere around here. Where exactly? Well, we can do a little bit of math. Because if we add them, negative 10 over 3 plus 1/4 and divide by 2, we can get the middle. So I'm going to do that. We're going to add negative 10 over 3 and 1/4, and we're going to divide it by 2. And we get negative 37 over 24. Which is approximately, if we round, negative 5.4. So let's call it negative 1.54. So negative 1.5 would be here, so we'll put our axis of symmetry right there. And again, we're approximating on our graph, but for our numerical answer, keeping the fraction makes it much nicer. And what else can we use? Well, we can use the y-intercept of negative 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, way down here. This scale, let's leave that for a second and find the rest of the vertex. Because we don't really know our scale yet. Our vertex might be really, really big. Let's find out. Let's take our axis of symmetry and plug it into our equation. This time I'm going to plug it into this equation because I think it might work out a little bit nicer. We've got 3. Our axis of symmetry is negative 37 over 12. Nope, 24. Plus 10. And 4. Negative 37 over 12. Minus 1. So we're just taking our factored form equation, plugging in our axis of symmetry. So we got 3 bracket. I kept it as my answer, so I'm just going to write answer. Plus 10 and 4 answer minus 1. I have that fraction answer from the last question stored in my calculator. And there we have a really, really ugly looking fraction. Don't often call fractions ugly, but this one, negative 1,849 over 48, which is approximately negative 38.5. So if we want, we can approximate our vertex. We have our actual optimal value and axis of symmetry, but we could use our approximate values to write our vertex. You can usually only graph to about a decimal place of accuracy. So there we have it. So if we want to fit negative 38.5 on this scale, we can't just go down by ones. Let's go down by 5s. So this will be negative 5, negative 10, negative 15, negative 20, negative 25, negative 30, negative 35, negative 40. So negative 38.5 would be here. And now our y-intercept of negative 10 will fit a little bit nicer because it would just be right here. So we can start to draw our parabola. This point we can even mirror to here. We can approximate, of course, and there is our equation. Y equals 12x squared plus 37x minus 10. Now, this question's about as ugly as this math can get. Graphing these quadratics, because everything worked out as an ugly decimal, and we had to approximate for basically everything we put on this graph, with the exception of our y-intercept. So if anything, this is as hard as these questions are going to get. Usually the factoring works out quite nice and you get x-intercepts like 1 and 7. And then your axis is a nice number like 3. Nope, 4, it'd be 4. And then you plug in 4 and you get a nice number for your vertex. But in these examples, they didn't work out like that, which is okay. Working with decimals and fractions is okay and something we're going to get really comfortable with, especially for next year. Okay, there's one more example, example 4. This is an application question. You could try it on your own if you'd like. Pause the video or just stick with it and we'll do this one together. A parabolic cross-section of an arch in front of a museum is modeled by the relation h equals negative d squared plus 9, where h is the height in meters above the ground and d is the distance from the center of the arch. How wide and how tall is the arch? Well, it would be most helpful if we could graph this. If we had a picture of what this looked like, we could probably answer these questions. So let's take our equation. This is our d and this is our h, just like our x and our y, and let's try to graph it. Well, how would we do that? Well, this, even though it doesn't look like it, is a difference of squares. How is it a difference of squares? Well, since there's a negative in front of our d squared term, we can start by common factoring the negative. And now we just have d squared minus 9. That's our difference of squares. The square root of d squared is d, the square root of 9 is 3, and we have a minus sign. So if we want to factor this, we get d minus 3 and d plus 3. Why does that help us? Well, if we want the d-intercepts or the x-intercepts, we would make the y or the h 0. Just like we've done in every other example we've done in this video. And now we take each bracket, set it equal to 0, and solve. In the first one we get 3. And in the second one, we get minus 3. What's the point of this? Well, these are our d-intercepts. I should have wrote 3. D-intercepts. 3, 0, and negative 3, 0. 1, 2, 3. 1, 2, 3. And at a height of 0, that'd be the ground. So this helps us answer our first question. How wide is the arch? The arch is 6 meters wide because it goes from negative 3 to positive 3. 3 units plus 3 more. Now how tall is the arch? We'd probably need to know the vertex. How do you find the vertex? Well, you find the axis of symmetry. Well, the axis of symmetry is right between these spots. Right between 3 and negative 3 is 0. So if we plug 0 into our equation, we should get the vertex. If you plug 0 in, 0 squared is 0, we just end up with 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And there is our arch. The other way we could have got 9, well, there's our c value. That's our y-intercept is 9. When you have a vertex on the x-axis, or sorry, y-axis, that's your y-intercept. Your vertex is your y-intercept. So now we can say, therefore, the arch is 9 meters tall. All right, that's it for graphing quadratics using x-intercepts. Thanks for watching, and I'll see you in 6.4.